Hello there and welcome to Sleep Knowledge. I'm so glad you're here tonight. The ground beneath your feet has a story billions of years old. Mountains rise and fall, continents drift like slow ships across the globe, and deep within the earth, forces powerful enough to reshape entire landscapes move in patient, relentless rhythms. Tonight we're exploring these quiet wonders together, the deep history of our planet, told at a pace perfect for drifting off. If these peaceful journeys help you unwind, consider liking and subscribing. It helps others find their way here too. Now settle in, let your shoulders soften, and let's begin. The earth beneath us is not solid in the way we imagine. Beneath the thin crust we walk on lies the mantle, a layer of rock so hot it flows like thick honey over geological time. This movement, imperceptibly slow to us, drives everything we see on the surface. Mountains, valleys, ocean trenches, volcanic islands, all of them are shaped by the restless motion of rock deep below. The outermost layer of Earth, the crust, is divided into massive pieces called tectonic plates. These plates float on the mantle beneath them, drifting at speeds measured in centimeters per year. Some move no faster than your fingernails grow. Yet over millions of years, this slow dance has rearranged entire continents, opened and closed oceans, and built mountain ranges that scrape the sky. There are 7 major tectonic plates and many smaller ones. The Pacific Plate, the largest, underlies most of the Pacific Ocean. The North American Plate carries not just the continent but part of the Atlantic Ocean floor as well. Where these plates meet, the Earth becomes restless. Earthquakes rumble, volcanoes erupt, mountains rise from the collision of continental masses. The theory of plate tectonics, which explains all this movement, is remarkably recent. It wasn't widely accepted until the 1960 seconds. Before then, scientists struggled to explain why fossils of the same ancient creatures appeared on continents separated by vast oceans. Why did the coastlines of Africa and South America fit together like puzzle pieces? The answer was that they once were together part of a supercontinent called Pangaea. Pangaea existed around 200 million years ago. All the landmasses we know today were joined in a single, massive continent surrounded by a global ocean called Panthalassa. Over time, Pangaea began to break apart. Rifts opened. Magma welled up from below. New ocean floor formed between the separating pieces. Africa drifted away from South America. India crashed into Asia. Australia split from Antarctica and journeyed north. This process continues today. The Atlantic Ocean grows wider by a few centimeters each year as new seafloor forms along the mid-Atlantic ridge. Meanwhile, the Pacific Ocean shrinks as its edges are swallowed beneath surrounding continents in subduction zones. In another 200 million years, the continents may reunite into a new supercontinent. Some scientists have even given it a name, Pangaea Ultima. Let that settle for a moment. The ground you stand on is moving, slowly but surely, toward a distant reunion, with lands now separated by oceans. Volcanoes are windows into the Earth's interior. When magma molten rock beneath the surface rises and erupts, it becomes lava. The violence or gentleness of an eruption depends on the magma's composition. Thick, viscous magma traps gases, building pressure until it explodes. Thin, runny magma allows gases to escape easily, producing calmer lava flows. The Ring of Fire encircles the Pacific Ocean, a zone where roughly 75% of the world's active volcanoes exist. This ring marks the edges of the Pacific Plate, where it collides with or slides beneath other plates. Subduction zones, where one plate dives beneath another, create the conditions for explosive volcanic activity. Water trapped in the descending plate melts the rock above it, generating magma that rises to form volcanoes. Mount St. Helens in Washington state erupted in 1980 with the force of 27,000 atomic bombs. The eruption removed over 1,000 feet from the mountain's summit and sent ash 17 miles into the atmosphere. Forests were flattened for miles. Yet within years, life returned. Plants pushed through the ash. Animals reclaimed the devastated landscape. Today, Mount St. Helens serves as a living laboratory for studying ecological recovery. Not all volcanoes are violent. The Hawaiian Islands were built by shield volcanoes, which produce gentle eruptions of thin, runny lava. These eruptions can last for years, slowly building broad, gently sloping mountains. The Big Island of Hawaii is still growing as Kilauea, one of the world's most active volcanoes, adds new land to its shores. Deep beneath Yellowstone National Park lies one of the world's largest supervolcanoes. The Yellowstone caldera is a massive volcanic crater formed by 3 colossal eruptions over the past 2 million years. The most recent eruption, 640,000 years ago, ejected enough material to bury Texas under 5 feet of ash. Today, the magma chamber beneath Yellowstone remains active, feeding the park's famous geysers and hot springs. Geysers like Old Faithful occur when groundwater seeps deep into the earth, is heated by magma, and returns to the surface as steam and boiling water. The precise timing of Old Faithful's eruptions once every 90 minutes or so comes from the specific geometry of underground chambers and channels. Each geyser has its own unique plumbing system. Earthquakes occur when stress built up along faults, cracks in the Earth's crust, is suddenly released. Tectonic plates don't slide past each other smoothly. They grind and stick, accumulating strain over years or centuries. When the stress exceeds the strength of the rocks, they break, and the stored energy radiates outward as seismic waves. The San Andreas Fault in California is one of the world's most famous faults. It marks the boundary between the Pacific Plate and the North American Plate, which slide past each other horizontally. Los Angeles, on the Pacific Plate, moves northward toward San Francisco, on the North American Plate, at about 2 inches per year. In roughly 15 million years, the two cities will be neighbors. Seismic waves come in several types. Primary waves, or P waves, are compression waves that travel through solid rock and liquid. They arrive first, moving quickly and causing a sharp jolt. Secondary waves, or S waves, are shear waves that move more slowly and only through solids. They produce a rolling motion. Surface waves, which travel along the Earth's crust, arrive last but cause the most damage, shaking the ground with large, slow undulations. The magnitude of an earthquake is measured on the moment magnitude scale, which replaced the older Richter scale. Each whole number increase represents roughly 30 times more energy released. A magnitude 7 earthquake releases about 1,000 times more energy than a magnitude 5. The largest earthquake ever recorded, a magnitude 9.5 in Chile in 1960, released more energy than all the world's nuclear weapons combined. Most earthquakes occur along plate boundaries, but some happen far from the edges. These intraplate earthquakes are less common, but can be just as destructive. The New Madrid earthquakes of 1811 and 1812, centered in Missouri, rang church bells in Boston, 1,000 miles away, and temporarily reversed the flow of the Mississippi River. Deep earthquakes occur hundreds of miles beneath the surface in subduction zones, where one plate descends into the mantle. At such depths, rocks behave differently. They're under immense pressure and temperature, yet they can still break suddenly, generating earthquakes that can be felt at the surface far above. After a major earthquake, aftershocks follow smaller earthquakes triggered by the redistribution of stress along the fault. Aftershocks can continue for months or even years. Occasionally, an aftershock can be nearly as large as the main shock, adding to the destruction. Imagine for a moment the patience of stone. A mountain range takes millions of years to rise. Each earthquake, each volcanic eruption, is a single heartbeat in a process almost too slow to comprehend. Fossils are the preserved remains or traces of ancient life. Most fossils form when organisms are buried quickly in sediment, mud, sand, or volcanic ash. Over time, minerals seep into the remains, replacing organic material with stone. The result is a perfect replica of the original organism, preserved in rock. The fossil record reveals the history of life on Earth. Single-celled organisms appeared roughly 3.5 billion years ago. For most of Earth's history, life remained microscopic. Then, around 540 million years ago, complex life exploded in diversity during the Cambrian explosion. Trilobites, ancient arthropods with segmented bodies and compound eyes, thrived in Cambrian seas. Their fossils are among the most common and beloved. Dinosaurs dominated the Earth for over 160 million years. They ranged from chicken-sized predators to long-necked giants weighing over 70 tons. The largest dinosaur ever discovered, Argentinosaurus, stretched over 100 feet from head to tail. Yet despite their size and success, the dinosaurs vanished suddenly 66 million years ago when an asteroid struck the Yucatan Peninsula, triggering mass extinction. That impact left a scar called the Chicxulub crater, over 100 miles wide. The asteroid, roughly 6 miles across, struck with the force of billions of nuclear bombs. The impact vaporized rock, sent tsunamis racing across oceans, and ejected so much debris into the atmosphere that sunlight was blocked for years. Plants died, food chains collapsed, 3/4 of Earth's species went extinct. But life persisted. Mammals, small and adaptable, survived in burrows and crevices. With the dinosaurs gone, they diversified rapidly, filling ecological niches left vacant. Eventually, primates emerged, and from them, humans. We exist because of that ancient catastrophe. Amber, fossilized tree resin, can preserve organisms in exquisite detail. Insects trapped in amber 40 million years ago look as if they died yesterday. Their delicate wings, antennae, even internal organs can be seen under a microscope. Some amber contains air bubbles from ancient atmospheres, offering clues about the Earth's climate long ago. Petrified wood forms when trees are buried in sediment, and groundwater rich in minerals flows through their tissues. Silica, the same mineral that forms quartz, replaces the organic material cell by cell. The result is wood turned to stone, often preserving growth rings, bark texture, even fossilized insects trapped inside. The petrified forest in Arizona contains logs over 200 million years old, their colors brilliant reds, oranges, and purples from iron and manganese. Coal is fossilized plant material, formed from ancient swamps and forests buried under sediment. Over millions of years, heat and pressure transformed the plant matter into carbon-rich coal. The coal we burn today is sunlight captured by plants hundreds of millions of years ago, stored in stone, and released in our power plants. Oil and natural gas also formed from ancient life, mostly microscopic plankton that lived in ancient seas. When these organisms died, they sank to the ocean floor and were buried under sediment. Heat and pressure transformed their remains into hydrocarbons. These liquid and gaseous fuels migrated through porous rock until trapped beneath impermeable layers, forming the oil and gas reservoirs we drill today. The study of fossils, paleontology, allows us to reconstruct entire ecosystems that no longer exist. We can determine what ancient creatures ate by examining their teeth and fossilized stomach contents. We can infer behavior from trackways' fossilized footprints. We can even analyze fossilized pollen to understand ancient climates and plant life. Sometimes fossils reveal transitional forms, species that show characteristics of two different groups. Tiktaalik, discovered in Arctic Canada, is a fish with wrist bones and a neck, representing a stage in the evolution of fish into land-dwelling tetrapods. Archaeopteryx, a fossil from Germany, has both feathers like a bird and teeth, and a bony tail like a dinosaur, illustrating the evolutionary link between dinosaurs and birds. Mass extinctions punctuate the fossil record. The Permian-Triassic extinction, 252 million years ago, was the most severe. Roughly 90% of marine species and 70% of terrestrial species vanished. The cause remains debated, but volcanic eruptions in Siberia, which lasted for millennia and released vast amounts of greenhouse gases, are a leading suspect. Each extinction reshaped life on Earth. After each catastrophe, survivors diversified, filling empty ecological roles. Evolution accelerated in the aftermath of destruction. The history of life is not a steady progression, but a series of expansions, collapses, and recoveries. Let that thought drift through your mind. Life on Earth has faced extinction again and again, yet it endures, adapts, and flourishes anew. Minerals are naturally occurring, inorganic solids with a defined chemical composition and crystalline structure. There are over 5,000 known minerals, each with unique properties. Some are common quartz, feldspar, mica. Others are rare and prized for their beauty: diamonds, emeralds, rubies. Quartz is one of the most abundant minerals on Earth. It's composed of silicon and oxygen, the two most common elements in the Earth's crust. Quartz crystals can be clear, milky white, purple amethyst, pink rose quartz, or yellow citrine. They form in a variety of environments, from volcanic rocks to sedimentary layers to veins in metamorphic rocks. Diamonds form deep within the Earth, over 100 miles beneath the surface, where pressures and temperatures are extreme. Carbon atoms bond in a rigid, three-dimensional lattice, creating the hardest natural substance known. Most diamonds are over 1 billion years old. They reach the surface through volcanic eruptions that occur in pipes of volcanic rock called kimberlite. Not all diamonds are clear. Some contain inclusions, tiny pockets of minerals or fluids trapped during formation. These inclusions offer geologists clues about conditions deep in the mantle. Some diamonds contain minerals that exist only at extreme depths, providing our only samples of the deep earth. Rubies and sapphires are both varieties of the mineral corundum, composed of aluminum and oxygen. Trace amounts of chromium give rubies their red color. Sapphires, which can be blue, yellow, pink, or green, owe their hues to iron and titanium. The finest rubies, called pigeon's blood for their deep red color, come from Myanmar. Kashmir sapphires, prized for their velvety blue, are among the most valuable gems. Emeralds are a variety of the mineral beryl, colored green by traces of chromium or vanadium. They form in hydrothermal veins where hot, mineral-rich fluids flow through cracks in rock. The finest emeralds come from Colombia, where they form in sedimentary rocks, a rare and special geological setting. Opals are unique among gemstones. Unlike most gems, which are crystalline, opals are amorphous. They lack a regular atomic structure. They form when silica-rich water seeps into cracks and cavities in rock and evaporates, leaving behind layers of microscopic silica spheres. These spheres diffract light, creating the opal's characteristic play of colors. Minerals form through several processes. Some crystallize from cooling magma, others precipitate from evaporating water. Think of salt flats, where halite, table salt, crystallizes as salty lakes dry up. Metamorphic minerals form when existing rocks are subjected to heat and pressure, transforming their minerals into new forms. Crystals grow when atoms arrange themselves in repeating patterns. The shape of a crystal reflects its internal atomic structure. Quartz forms 6-sided prisms. Halite forms cubes. Pyrite, or fool's gold, forms cubes or 12-sided crystals called pyridohedrons. Each mineral has its own preferred crystal shape. Geodes are rocks with hollow cavities lined with crystals. They form when gas bubbles in volcanic rock or cavities in sedimentary rock are filled with mineral-rich water. Over time, crystals grow inward from the walls, creating a glittering interior. Cracking open a geode reveals a hidden treasure: crystals that have grown in darkness for millions of years. Some minerals glow under ultraviolet light, a property called fluorescence. Fluorite, for which the phenomenon is named, glows blue or green. Calcite can glow red, blue, or yellow depending on impurities. Willemite, a zinc silicate, glows brilliant green. Collecting fluorescent minerals is a popular hobby, revealing a hidden world of color invisible to the naked eye. Minerals are more than beautiful, they're essential to modern life. Iron ore provides steel for buildings and machines. Copper is used in electrical wiring. Lithium, extracted from mineral deposits, powers batteries in phones and electric vehicles. Sand, mostly quartz, is used to make glass and concrete. Our entire technological civilization rests on minerals extracted from the earth. Gold, one of the first metals humans discovered, is chemically inert. It doesn't corrode or tarnish. It's also incredibly rare. All the gold ever mined would fit into a cube roughly 70 feet on each side. Most of Earth's gold sank to the core during the planet's formation. The gold we find in the crust arrived later, delivered by asteroid impacts billions of years ago. Silver tarnishes because it reacts with sulfur compounds in the air, forming silver sulfide. This is why silver jewelry darkens over time. Yet silver is the best conductor of electricity of all metals, making it invaluable in electronics. Let your thoughts drift like crystals forming in a hidden cave. Slowly, patiently, each facet catching light in the darkness. Mountains rise through several processes. Some form when tectonic plates collide, crumpling and thrusting rock upward. The Himalayas are still rising as the Indian plate crashes into the Eurasian plate, growing taller by about 5 millimeters each year. Mount Everest, the world's tallest mountain, stands over 29,000 feet above sea level, yet it's still climbing. Before the Himalayas, other mountain ranges rose and eroded away. The Appalachian Mountains in eastern North America are ancient. Formed around 480 million years ago when continents collided to form the supercontinent Pangaea. Once as tall as the Himalayas, they've been worn down by erosion. Their rounded peaks and gentle slopes are the remnants of mountains that once rivaled the Alps. Volcanic mountains form differently. They're built from layers of lava and ash erupted from vents. Mount Fuji in Japan, Kilimanjaro in Tanzania, Mount Rainier in Washington, all are volcanic mountains. Some volcanic mountains are isolated peaks fed by plumes of hot mantle rock rising from deep within the earth. The Hawaiian Islands are examples, each island a volcanic mountain rising from the ocean floor. The tallest mountain in the solar system is not on Earth. Olympus Mons on Mars rises nearly 17 miles above the Martian surface, more than twice the height of Everest. It's a shield volcano, similar to those in Hawaii but vastly larger, built by countless eruptions over millions of years. Mountains influence weather and climate. When moist air rises over a mountain range, it cools and condenses, producing rain or snow on the windward side. The leeward side, in the mountain's rain shadow, receives little precipitation. Deserts often exist downwind of major mountain ranges. The Atacama Desert in Chile, one of the driest places on Earth, lies in the rain shadow of the Andes. Glaciers carve mountains, sculpting valleys and sharpening peaks. During ice ages, glaciers advance, grinding rock into powder and carving deep U-shaped valleys. When glaciers retreat, they leave behind moraines, piles of rock and debris. The Great Lakes in North America were carved by glaciers during the last ice age. The deep, steep-sided fjords of Norway and New Zealand are glacial valleys flooded by the sea. The Matterhorn, one of the most iconic peaks in the Alps, owes its pyramid shape to glacial erosion. Glaciers carved cirques, bowl-shaped depressions into the mountain from multiple sides. Where these cirques met, they left a sharp peak. Mountains are constantly eroding. Rain, wind, ice, and gravity all work to wear them down. Rockfalls, landslides, and avalanches carry material downslope. Rivers carry sediment to the sea. Over millions of years, mountains are leveled, and the sediment becomes new rock elsewhere. Deep within mountain ranges, rocks undergo metamorphism. Heat and pressure transform limestone into marble, sandstone into quartzite, shale into slate. The deeper the rock is buried, the more intense the metamorphism. Some rocks, buried 50 miles deep, melt partially, producing migmatites, rocks that are part solid, part once molten. Some mountain ranges contain ophiolite, slices of ancient ocean floor thrust onto continents during collisions. These rocks, formed at mid-ocean ridges, are now found high in the mountains, far from any sea. Studying ophiolites gives geologists a rare chance to examine oceanic crust without drilling through miles of ocean water. Imagine standing on a mountaintop, looking out over peaks stretching to the horizon. Each peak is a monument to forces operating over timescales we can barely grasp. They rise, they endure, they fall, and yet while they stand, they touch the sky. Oceans cover more than 70% of Earth's surface. The Pacific Ocean alone is larger than all of Earth's land masses combined. The average depth of the ocean is over 12,000 feet. But the deepest point, the Challenger Deep in the Mariana Trench, plunges nearly 36,000 feet deep, enough to swallow Mount Everest with a mile to spare. The ocean floor is not flat. It has mountains, valleys, volcanoes, and vast plains. The mid-ocean ridge, a continuous underwater mountain range, stretches over 40,000 miles, encircling the globe like the seam on a baseball. Here, tectonic plates pull apart, and magma rises to create new oceanic crust. This is where the seafloor is born. Hydrothermal vents, found along mid-ocean ridges, spew superheated water rich in minerals. Despite the extreme conditions, temperatures over 700 degrees Fahrenheit, crushing pressure, total darkness, life thrives here. Bacteria feed on chemicals in the vent fluids, forming the base of an ecosystem independent of sunlight. Giant tube worms, eyeless shrimp, and ghostly crabs live in these deep-sea oases. The discovery of hydrothermal vents in the 1970 seconds revolutionized biology. It proved that life doesn't require sunlight. On Earth, nearly all life depends ultimately on photosynthesis. But at hydrothermal vents, chemosynthesis powers the food chain. This discovery has profound implications for the search for life on other worlds, where sunlight may be scarce but chemical energy could be abundant. Ocean trenches form where one tectonic plate is forced beneath another in subduction zones. The Mariana Trench marks where the Pacific Plate dives beneath the Mariana Plate. Trenches are the deepest parts of the ocean, cold, dark, and under immense pressure. At the bottom of the Challenger Deep, the pressure is over 16,000 pounds per square inch, equivalent to having 50 jumbo jets stacked on top of you. Despite the extreme conditions, life exists even in the deepest trenches. Amphipods, small crustaceans, have been found at the bottom of the Mariana Trench. Fish, though rare at such depths, have been observed over 26,000 feet down. These creatures have adaptations. We're only beginning to understand proteins and cell membranes that function under pressures that would crush most life. Seamounts are underwater volcanoes that don't reach the surface. There are tens of thousands of seamounts in the world's oceans. They create isolated habitats, and many support unique ecosystems. Corals, sponges, and fish cluster around seamounts, feeding on nutrients stirred up by currents. Some seamounts are ancient extinct volcanoes that erupted millions of years ago and now sit silent on the ocean floor. When seamounts do break the surface, they become islands. The Hawaiian Islands are the tops of massive volcanic mountains rising from the ocean floor. From base to summit, Mauna Kea in Hawaii is taller than Everest, over 33,000 feet. Most of it is hidden beneath the waves. Ocean currents are rivers in the sea, driven by wind, temperature, and salinity. The Gulf Stream, a warm current flowing from the Gulf of Mexico up the eastern coast of North America and across the Atlantic, carries more water than all the rivers on Earth combined. It moderates the climate of Western Europe, keeping it warmer than regions at similar latitudes elsewhere. The global ocean conveyor belt, or thermohaline circulation, moves water around the world. Warm surface water flows toward the poles. As it cools and freezes, it becomes saltier and denser, sinking to the ocean floor. This deep water flows toward the equator, where it eventually rises and completes the cycle. The entire loop takes about 1,000 years. Turbidity currents are underwater avalanches of sediment and water. Triggered by earthquakes or sediment buildup on continental slopes, they race down submarine canyons at speeds over 50 miles per hour. Turbidity currents carve canyons into the seafloor and deposit sediment in deep basins. Some submarine cables have been broken by turbidity currents, disrupting communication across oceans. The seafloor is a graveyard. Dead organisms drift down from the surface in a slow, constant rain called marine snow. On the ocean floor, this organic material accumulates, forming sediment. Some seafloor sediments are oozes, soft, muddy deposits made mostly of microscopic shells. Calcareous ooze contains shells of foraminifera and coccolithophores. Siliceous ooze contains the remains of diatoms and radiolarians. Beneath the sediment lies rock. Drilling into this rock has revealed a continuous record of Earth's climate going back millions of years. Oxygen isotopes in fossilized shells record ocean temperatures. Pollen and microfossils reveal what lived in the past. Ice cores from Antarctica and Greenland preserve samples of ancient atmosphere. Together, these records tell the story of Earth's changing climate. Take a breath. Let the rhythm of your breathing match the slow circulation of ocean currents, moving patiently, ceaselessly, shaping the world. Continental drift, the movement of continents over geological time, was once dismissed as pseudoscience. When Alfred Wegener proposed the theory in 1912, most scientists rejected it. Wegener had compelling evidence the fit of continents, matching fossils, similar rock formations on opposite sides of oceans, but he couldn't explain how continents moved. He died in 1930, his theory largely ignored. The breakthrough came in the 1960 seconds with the discovery of seafloor spreading. Scientists mapping the ocean floor found that the youngest rocks were at mid-ocean ridges, and the rocks got older with distance from the ridge. Magnetic stripes in the seafloor, caused by reversals in Earth's magnetic field, provided a timeline. The evidence was undeniable. The seafloor was spreading, and continents were moving. Plate tectonics unified geology. Suddenly, earthquakes, volcanoes, mountain building, and continental drift all made sense. They were different expressions of the same underlying process, the movement of tectonic plates. It was one of the great scientific revolutions, comparable to the theory of evolution or the discovery of DNA. The Wilson cycle describes the life cycle of ocean basins. It begins with rifting, where a continent splits apart. Magma rises, creating new oceanic crust. The rift widens into a narrow sea, then an ocean. Eventually, subduction begins and the ocean basin starts to close. Continents collide, mountain ranges rise, and the ocean disappears. The cycle takes hundreds of millions of years. The Red Sea is a young ocean, still in the early stages of the Wilson cycle. It formed as Africa and the Arabian Peninsula pulled apart. In another few million years, it may become as wide as the Atlantic. The Mediterranean Sea, by contrast, is closing. Africa is drifting northward toward Europe. In 50 million years, the Mediterranean may vanish entirely, crushed between colliding continents. The Himalayas are still rising, but they won't rise forever. Erosion limits mountain height. As mountains grow, they become steeper, and erosion accelerates. Eventually, erosion balances uplift, and the mountains stop growing. This equilibrium height depends on factors like rock strength and climate. The Himalayas may still grow for millions of years, but eventually erosion will win. India's journey northward over the past 50 million years is one of the most dramatic movements in recent geological history. Once part of the southern supercontinent Gondwana, India broke away and raced northward at speeds of up to 6 inches per year, fast for continental drift. When it collided with Asia, the impact crumpled the crust, lifting the Tibetan Plateau and the Himalayas. The Tibetan Plateau, the highest and largest plateau on Earth, averages over 15,000 feet in elevation. It's sometimes called the Third Pole because it holds the largest store of ice outside the Arctic and Antarctic. The plateau influences weather across Asia. The summer monsoon, which brings rain to billions of people, is driven in part by heating of the Tibetan Plateau. Antarctica was not always frozen. 50 million years ago, it was covered in forests and teeming with life. Fossils of ferns, dinosaurs, and even marsupials have been found there. Antarctica drifted southward and settled over the South Pole. As it became isolated from other continents, ocean currents changed, and the continent cooled. Ice sheets formed, eventually covering the entire landmass in ice up to 3 miles thick. Australia is the fastest moving continent today, drifting northward at about 3 inches per year. In 50 million years, it may collide with Southeast Asia, creating a new mountain range. The movement of Australia is driven by the subduction of the Pacific Plate beneath the Mariana Trench and other trenches to the north. Supercontinents have formed and broken apart multiple times in Earth's history. Before Pangaea, there was Rodinia, which formed around 1 billion years ago. Before Rodinia was another supercontinent, and before that another. The cycle repeats every 400 to 600 million years. Continents collide, merge, stay together for a time, then rift and drift apart, only to collide again in different configurations. Plate tectonics may be unique to Earth, at least in our solar system. Venus, similar in size to Earth, shows no evidence of plate tectonics. Its surface is dominated by volcanic plains, and its crust is a single unbroken shell. Mars once had tectonic activity, but it ceased billions of years ago. Earth's plate tectonics may be connected to the presence of water, which lubricates subduction zones and allows plates to move more easily. The movement of continents has shaped life on Earth. When continents merge, land-dwelling species can migrate and compete. When continents separate, populations are isolated and evolve independently. The unique animals of Australia, marsupials, monotremes, evolved in isolation after Australia separated from Antarctica and drifted northward. The breakup of Pangaea changed ocean currents and climates, triggering extinction events and evolutionary radiations. The collision that formed the Himalayas changed atmospheric circulation, intensifying the monsoon and drying Central Asia. The positions of continents influence where ice sheets form, where deserts develop, and where life thrives. Let that thought drift with you. The continents beneath our feet are wanderers, moving imperceptibly but inexorably, carrying life on their backs across a restless planet. Earth's history stretches back 4.5 billion years. The planet formed from a disk of gas and dust surrounding the young Sunday. Gravity pulled material together, and countless collisions of smaller bodies, called planetesimals, built up Earth's mass. The energy from these impacts melted the surface, creating a magma ocean. As Earth cooled, the heaviest elements, iron and nickel, sank to the center, forming the core. Lighter materials rose to form the mantle and crust. This process, called differentiation, gave Earth its layered structure. The core generates Earth's magnetic field, which protects the planet from solar wind and cosmic radiation. The Moon likely formed from debris ejected when a Mars-sized body, sometimes called Theia, collided with Earth. The impact vaporized rock, creating a disk of debris around Earth. This debris coalesced into the Moon. Evidence for this theory includes the Moon's low density, its lack of a large iron core, and the similar composition of moon rocks and Earth's mantle. Early Earth was hostile to life as we know it. The atmosphere lacked oxygen and was rich in carbon dioxide, methane, and ammonia. The surface was bombarded by asteroids and comets. Yet by 3.5 billion years ago, life had emerged. The first organisms were simple, single-celled, and anaerobic. They didn't need oxygen. The appearance of photosynthesis changed everything. Cyanobacteria, ancient bacteria that could harness sunlight to produce energy, began releasing oxygen as a waste product. Over hundreds of millions of years, oxygen accumulated in the atmosphere, poisoning many anaerobic organisms, but creating opportunities for new life. This event, the Great Oxidation Event, occurred around 2.5 billion years ago. Banded iron formations, ancient sedimentary rocks, with alternating layers of iron-rich and silica-rich minerals, record this transition. Dissolved iron in the oceans reacted with oxygen produced by cyanobacteria, forming iron oxide that settled to the seafloor. Once the ocean's iron was exhausted, oxygen began accumulating in the atmosphere. Life remained mostly microscopic for billions of years. Then, around 600 million years ago, complex multicellular life appeared. The Ediacaran biota, strange soft-bodied organisms unlike anything alive today, covered the seafloor. Some resembled ferns, others quilted mattresses. Their relationship to modern animals is uncertain. They may represent an early failed experiment in complex life. The Cambrian explosion followed, a burst of evolutionary innovation that produced most major animal groups within a relatively short time, tens of millions of years. Predation became common, leading to an evolutionary arms race of shells, spines, and protective armor. The world's oceans filled with life. Life moved onto land around 450 million years ago. Plants colonized the continents first, followed by arthropods, and eventually vertebrates. Early land plants were small, hugging the ground. Over time, they evolved taller forms, eventually producing forests. The evolution of trees changed the planet, drawing carbon dioxide from the atmosphere and cooling the climate. Oxygen levels have fluctuated throughout Earth's history. During the Carboniferous period, roughly 300 million years ago, oxygen levels reached 35%, compared to 21% today. Insects thrived in this oxygen-rich atmosphere, growing to enormous sizes. Dragonflies with wingspans over 2 feet patrolled the skies. Millipedes grew over 6 feet long. The Permian-Triassic extinction, the most severe mass extinction, may have been caused by volcanic eruptions in Siberia that lasted for millennia. These eruptions released carbon dioxide, methane, and sulfur dioxide, triggering global warming, ocean acidification, and acid rain. The extinction reshaped life on Earth, paving the way for the rise of dinosaurs. The dinosaurs' reign ended with the asteroid impact 66 million years ago. But before that, they dominated for over 160 million years longer than mammals have existed. They evolved into an astonishing variety of forms, from tiny feathered predators to giants that shook the ground with each step. Mammals survived the extinction and diversified rapidly. Primates appeared around 60 million years ago. Our hominin ancestors diverged from other apes around 6 million years ago. Homo sapiens, modern humans, emerged roughly 300,000 years ago in Africa. We are newcomers on a planet with a deep and complex history. Breath in, breath out. You are a thread in a story 4.5 billion years long. You are stardust, assembled into a form that can wonder at its own existence. And so here we are, gently gliding back from our journey through the deep history of Earth. We've explored the restless movement of continents, the fiery birth of mountains, the silent growth of crystals in the dark, and the endless churn of stone and time. You are part of this story too. The calcium in your bones was forged in the heart of a dying star. The iron in your blood was scattered across space by a supernova. The atoms in your body have been recycled through countless forms: mountains, oceans, forests, creatures long extinct before becoming you. Ice ages have shaped Earth's surface repeatedly over the past 2.5 million years. During glacial periods, ice sheets kilometers thick covered much of North America, Europe, and Asia. These glaciers advanced and retreated in cycles roughly every 100,000 years, driven by subtle changes in Earth's orbit and tilt. The most recent ice age peaked about 20,000 years ago. Ice covered Canada, the northern United States, Scandinavia, and much of Britain. Sea levels dropped over 400 feet as water was locked up in ice sheets. Land bridges appeared, allowing humans and animals to migrate between continents. The ancestors of Native Americans crossed from Asia to North America over the Bering Land Bridge. When the ice retreated, it left behind a transformed landscape. The weight of ice sheets was so great that it actually depressed the Earth's crust. Today, regions like Scandinavia and Canada are still rebounding upward, rising a few millimeters each year as the crust slowly recovers. This process, called isostatic rebound, will continue for thousands of years. Glacial erratics are boulders carried by glaciers and deposited far from their source. Some erratics weigh thousands of tons. They puzzle early geologists who couldn't imagine how such massive rocks could have traveled hundreds of miles. The answer, glacial transport, wasn't accepted until the theory of ice ages became established in the 19th century. Fjords are deep, narrow inlets carved by glaciers. As glaciers flowed down valleys toward the sea, they carved deep channels. When the glaciers retreated and sea levels rose, these channels flooded, creating fjords. Norway's coastline is famous for its fjords, some over 4,000 feet deep. Fjords exist on every continent, evidence of past glaciation. Caves form in several ways. Limestone caves, the most common, are carved by slightly acidic groundwater. As water seeps through soil, it absorbs carbon dioxide, forming carbonic acid. This weak acid dissolves limestone over thousands of years, creating underground passages and chambers. Stalactites grow downward from cave ceilings, deposited drip by drip. Stalagmites grow upward from cave floors. When they meet, they form columns. The longest cave system in the world is Mammoth Cave in Kentucky, with over 400 miles of explored passages. New sections are still being discovered. Some caves contain underground rivers. Others have vast chambers large enough to hold entire city blocks. Cave ecosystems are unique, adapted to total darkness and limited food. Blind fish, albino crayfish, and specialized insects thrive in this lightless world. Karst landscapes form in regions with soluble rock like limestone. Sinkholes, caves, underground rivers, and disappearing streams characterize karst terrain. When cave roofs collapse, sinkholes open suddenly at the surface. Some sinkholes are small pits, others are massive depressions hundreds of feet across and deep. The Great Blue Hole off the coast of Belize is a collapsed underwater cave over 1,000 feet wide and 400 feet deep. Deserts cover about 1/3 of Earth's land surface. They form in several ways. Some deserts, like the Sahara, exist in subtropical high-pressure zones where descending air warms and dries. Others form in rain shadows of mountain ranges. Still others, like the Atacama Desert in Chile, lie along coasts where cold ocean currents cool the air, preventing cloud formation. The Sahara Desert was not always arid. 10,000 years ago it was a green savanna with lakes, rivers, and abundant wildlife. Rock art from this period shows hippos, giraffes, and elephants. Changes in Earth's orbit altered rainfall patterns, and the Sahara gradually dried. Archaeological evidence suggests that the desertification drove human migrations, possibly influencing the development of Egyptian civilization along the Nile. Sand dunes form when wind blows sand into piles. The shape of a dune depends on wind direction and sand supply. Crescent-shaped Barkhan dunes form in areas with limited sand and consistent wind. Linear dunes, running parallel to prevailing winds, can stretch for miles. Star dunes, with arms radiating from a central peak, form where winds blow from multiple directions. Sand grains in deserts are remarkably well sorted and rounded. Wind is a more selective transporter than water, carrying only grains within a narrow size range. Over time, the constant collisions during wind transport round the grains. Some desert sand is over 99% quartz, one of the hardest and most durable minerals. Singing sands, found in some deserts and beaches, produce musical tones when disturbed. The sound, which can be loud enough to hear miles away, comes from grains of a specific size and shape sliding past each other. The mechanism isn't fully understood, but it involves resonance within the sand layer. Marco Polo described singing sands in the Gobi Desert centuries ago, attributing the sound to spirits. Rivers shape the land through erosion and deposition. They carve valleys, transport sediment, and create floodplains. The Grand Canyon, carved by the Colorado River, exposes nearly 2 billion years of Earth's history in its walls. The canyon is over a mile deep, cut layer by layer as the river eroded downward, while the Colorado Plateau uplifted. Meanders are looping curves that rivers form in flat terrain. Rivers naturally erode the outside of curves, where water flows faster, and deposit sediment on the inside, where it flows slower. Over time, meanders migrate downstream and grow more pronounced. Sometimes a meander loop is cut off, forming an oxbow lake, a curved lake separated from the main channel. Deltas form where rivers meet the sea and deposit their sediment. The Mississippi River Delta has been building for thousands of years, creating new land as sediment accumulates. Deltas are among the most fertile landscapes on Earth, but they're also vulnerable. Sediment starvation, caused by dams upstream, can cause deltas to erode and sink. The Mississippi Delta is losing land at an alarming rate. Alluvial fans are fan-shaped deposits that form where steep mountain streams reach flat valleys. The sudden decrease in slope causes the stream to drop its sediment. Alluvial fans are common in arid regions, where flash floods carry large amounts of debris from mountains to valleys. Badlands are heavily eroded landscapes with little vegetation. Soft sedimentary rocks, carved by water and wind, create a maze of ridges, gullies, and colorful layers. The Badlands of South Dakota expose ancient sediments containing abundant fossils from the Oligocene epoch, 30 million years ago. Early paleontologists flocked to the region, discovering saber-toothed cats, ancient horses, and giant pigs. Weathering breaks down rock at Earth's surface. Mechanical weathering physically breaks rocks without changing their composition. Freeze-thaw cycles, where water freezes and cracks and expands, are a powerful form of mechanical weathering in cold climates. Chemical weathering alters rock composition through reactions with water, oxygen, and acids. Biological weathering involves living organisms. Plant roots grow into cracks, widening them as they expand. Lichens, fungi, and bacteria produce acids that dissolve minerals. Burrowing animals mix and aerate soil, accelerating weathering. Termites in tropical regions can move tons of soil, bringing fresh minerals to the surface. Soil is a mixture of weathered rock, organic matter, air, and water. It forms slowly, often taking hundreds of years to build an inch. Soil supports most terrestrial life, yet it's easily lost. Erosion, particularly on steep slopes or where vegetation is removed, can strip away soil in a single storm. Some civilizations have collapsed after degrading their soils through overuse. Sediment carried by rivers eventually reaches the ocean, where it settles layer by layer on the seafloor. Over millions of years, these layers are buried, compacted, and cemented into sedimentary rock. Sandstone forms from sand, shale from mud, and limestone from calcium carbonate, often from the shells of marine organisms. Sedimentary rocks preserve a record of past environments. Ripple marks indicate ancient currents. Mud cracks reveal tidal flats that dried in the sun. Fossilized raindrops, salt crystals, and even dinosaur footprints are preserved in stone. Geologists read these clues like pages in a book, reconstructing landscapes that existed millions of years ago. Coal swamps dominated landscapes during the Carboniferous period. Giant ferns, horsetails, and club mosses, relatives of today's small plants, grew over 100 feet tall. When these plants died, they fell into stagnant water where oxygen was scarce. Instead of decaying completely, they accumulated as peat. Buried under sediment, the peat was compressed and heated, transforming into coal. The Carboniferous forests pulled vast amounts of carbon dioxide from the atmosphere, storing it underground as coal. This drawdown of greenhouse gases may have triggered an ice age. Glaciers formed at the South Pole, and sea levels fluctuated as ice sheets advanced and retreated. Chalk, a soft white limestone, is made almost entirely of the microscopic shells of coccolithophores, single-celled algae that lived in ancient seas. The White Cliffs of Dover in England are pure chalk, formed from the accumulated remains of countless billions of these tiny organisms. The chalk deposits are hundreds of feet thick, representing millions of years of slow accumulation. Flint, often found in chalk, forms from silica that precipitated in nodules within the sediment. Ancient humans prized flint for tool-making. When struck, it fractures with sharp edges, perfect for cutting. Flint tools, millions of years old, are among the earliest evidence of human technology. Gypsum is a soft mineral that forms when seawater evaporates. Ancient seas that dried up left behind vast deposits of gypsum. The white sands of New Mexico are made of gypsum crystals, eroded from nearby mountains and blown into dunes. Unlike quartz sand, gypsum doesn't absorb much heat, so the dunes remain cool even under the desert sun. Salt domes form when buried salt, less dense than surrounding rock, rises slowly through overlying layers like a balloon through water. As it rises, it deforms the rock above, creating domes and traps where oil and natural gas can accumulate. Many of the world's major oil fields are associated with salt domes. The rock cycle describes how rocks transform from one type to another over geological time. Igneous rocks form from cooling magma. Weathering and erosion break them down into sediment, which lithifies into sedimentary rocks. Heat and pressure transform sedimentary rocks into metamorphic rocks. If buried deep enough, metamorphic rocks melt, producing magma that can crystallize into igneous rocks again. Some rocks complete the cycle quickly, geologically speaking. Volcanic rocks can be weathered, transported, deposited, and buried within a few million years. Other rocks take hundreds of millions of years to move through the cycle. Some ancient rocks, over 3 billion years old, have been through the cycle multiple times. The oldest rocks on Earth are over 4 billion years old, found in remote regions of Canada, Australia, and Greenland. These rocks are survivors, fragments of Earth's earliest crust. Most rocks from that era have been recycled through plate tectonics and erosion. The few that remain offer precious glimpses of a young Earth vastly different from the planet we know. Zircon crystals, tiny and nearly indestructible, are the oldest minerals found on Earth. Some zircons are over 4.4 billion years old, older than any rock. They formed in magma and survived countless cycles of weathering, erosion, and reburial. Studying zircons, scientists have learned that liquid water existed on Earth's surface far earlier than once thought, perhaps within a few 100 million years of the planet's formation. Earth's magnetic field is generated by the motion of liquid iron in the outer core. As the planet rotates, convection currents in this molten metal generate electric currents, which in turn produce the magnetic field. This process, called the geodynamo, has operated for at least 3.5 billion years. The magnetic field is not constant. It waxes and wanes in strength, and occasionally it reverses magnetic north and south swap places. These reversals occur every few 100,000 years on average, though the timing is irregular. During a reversal, the field weakens significantly, and the poles can wander erratically before settling in their new positions. Magnetic reversals are recorded in rocks. When magma cools and solidifies, magnetic minerals within it align with Earth's magnetic field, locking in the direction like a compass frozen in time. By studying these magnetic records in rocks of different ages, geologists have reconstructed the history of Earth's magnetic field, revealing hundreds of reversals over hundreds of millions of years. The cause of magnetic reversals isn't fully understood. They appear to be random, influenced by chaotic processes in the fluid core. Some reversals happen quickly, perhaps in less than a century. Others take thousands of years. During a reversal, the magnetic field weakens, and the protection it provides from solar wind and cosmic radiation diminishes. Some scientists have speculated that reversals may have influenced evolution by increasing mutation rates, though evidence is inconclusive. Aurora borealis and aurora australis, the northern and southern lights, are visible manifestations of Earth's magnetic field interacting with the solar wind. Charged particles from the sun spiral along magnetic field lines toward the poles, where they collide with atmospheric gases, causing them to glow. Oxygen produces green and red hues. Nitrogen produces blue and purple. The result is a shimmering curtain of light dancing across the polar skies. Auroras occur on other planets too. Jupiter's auroras, powered by its immense magnetic field and volcanic moon Io, are 1,000 times more powerful than Earth's. Saturn, Uranus, and Neptune also have auroras. Studying these planetary auroras helps scientists understand how magnetic fields interact with solar wind across the solar system. Lightning is a form of atmospheric electricity. Within thunderstorms, collisions between ice particles and water droplets transfer electric charge. Positive charges accumulate near the cloud top, negative charges near the bottom. The electric potential grows until it overcomes the air's resistance, and a discharge occurs: lightning. A lightning bolt can heat the surrounding air to 50,000 degrees Fahrenheit, hotter than the surface of the Sunday. The rapid expansion of air creates a shock wave we hear as thunder. Light travels faster than sound, so we see lightning before hearing thunder. Counting the seconds between flash and rumble gives a rough estimate of distance: 5 seconds per mile. Lightning doesn't only strike downward. It also flashes within clouds, and from clouds to the upper atmosphere. Sprites, elves, and blue jets are exotic forms of lightning that occur above thunderstorms. Sprites are brief red flashes. Elves are expanding rings of light. Blue jets shoot upward from cloud tops. These phenomena were only confirmed in recent decades, captured by high-altitude aircraft and the International Space Station. Fulgurites are natural glass tubes formed when lightning strikes sand. The intense heat over 3,000 degrees Fahrenheit melts the sand instantly. As it cools, it solidifies into a hollow tube, often branching like the lightning bolt itself. Fulgurites can be several feet long, fragile and beautiful, preserved in deserts and beaches around the world. Meteorite impacts have shaped Earth's history. While most asteroids burn up in the atmosphere, a few reach the surface. Large impacts are rare but catastrophic. The asteroid that ended the age of dinosaurs was roughly 6 miles across. Smaller impacts occur more frequently, leaving craters across the planet. Meteor Crater in Arizona, about 4,000 feet across and over 500 feet deep, was formed 50,000 years ago by an iron meteorite. The impact released energy equivalent to 10 megatons of TNT, devastating the surrounding area. The crater is well preserved in the arid climate, one of the best studied impact sites on Earth. Most impact craters on Earth have been erased by erosion, plate tectonics, and sedimentation. Yet geologists have identified over 100 craters worldwide, ranging from small pits to massive structures over 100 miles across. The Sudbury Basin in Canada and the Vredefort Dome in South Africa are ancient impact structures over 1 billion years old, deeply eroded but still recognizable. Impact events can trigger massive environmental changes. The Chicxulub impact ejected dust and aerosols that blocked sunlight, cooling the planet and disrupting food chains. Wildfires ignited by falling debris raged across continents. Tsunamis, hundreds of feet high, swept over coastlines. The combined effects led to the extinction of 3/4 of Earth's species. But impacts also bring materials from space. Water and organic molecules delivered by comets and asteroids may have contributed to the emergence of life on Earth. Some scientists propose that life's building blocks, amino acids, sugars, nucleotides, arrive from space, seeding a sterile planet with the ingredients for biology. Tectites are small, glassy objects formed by meteorite impacts. When an asteroid strikes, it melts rock and ejects molten droplets into the air. These droplets cool and solidify during flight, forming tectites with distinctive shapes, spheres, teardrops, dumbbells. Tectites are found in strewn fields, areas where thousands or millions of them landed. Their chemistry reveals the composition of the target rock, offering clues about impact events. Comets are icy bodies that orbit the Sun. When they approach the inner solar system, solar heat vaporizes their ice, creating glowing tails of gas and dust. Comets originate in the Kuiper Belt and Oort cloud, distant reservoirs of icy debris left over from the solar system's formation. Occasionally, gravitational perturbations send a comet sunward, where it becomes visible from Earth. Impact craters on other planets and moons reveal their histories. The Moon, lacking an atmosphere and plate tectonics, preserves a record of impacts spanning 4 billion years. Its heavily cratered surface tells of a violent early solar system when planetary formation was still ongoing and collisions were frequent. Mercury, Mars, and many moons are similarly scarred. The Late Heavy Bombardment, a period of intense impacts about 4 billion years ago, pummeled the inner solar system. Earth was struck repeatedly, possibly vaporizing its oceans temporarily. The Moon's largest basins, visible as dark patches, formed during this time. The cause of the bombardment remains debated, but it may have been triggered by migrations of the giant planets, whose gravity perturbed countless asteroids and comets inward. Take a breath. Imagine the night sky, not as distant stars, but as a reminder of Earth's place in a dynamic, sometimes violent, solar system. We orbit a star in a galaxy containing hundreds of billions of stars, in a universe with trillions of galaxies. And yet, here we are, on a planet that has sheltered life for billions of years. Hotspots are volcanic regions fed by plumes of hot mantle rock rising from deep within the Earth. Unlike most volcanoes, which occur at plate boundaries, hotspots are found in the middle of tectonic plates. The Hawaiian Islands are the most famous example. As the Pacific Plate moves northwest over a stationary hotspot, it creates a chain of volcanic islands. The Big Island of Hawaii, currently over the hotspot, is volcanically active. Older islands to the northwest are extinct, eroded, and subsiding. The Yellowstone hotspot has been active for over 16 million years. As the North American plate moved southwest over the hotspot, the path of volcanism progressed northeast, forming a track across the landscape. Yellowstone's caldera is the latest in this series. The hotspot will eventually emerge farther northeast, creating new volcanic centers while Yellowstone cools. Flood basalts are vast outpourings of lava that cover huge areas. The Deccan Traps in India, the Siberian Traps in Russia, and the Columbia River Basalt Group in the northwestern United States are examples. These eruptions released enormous volumes of lava, sometimes over hundreds of thousands of square miles in relatively short periods. Flood basalts are associated with mass extinctions, as the eruptions released greenhouse gases and sulfur compounds that altered global climates. The Siberian Traps eruption, which occurred around the time of the Permian-Triassic extinction, released enough lava to cover an area the size of Europe. The eruptions lasted for roughly 1 million years, pumping carbon dioxide and sulfur dioxide into the atmosphere. The resulting environmental changes, global warming, ocean acidification, acid rain devastated life on Earth. Volcanic gases can be deadly. Carbon dioxide, heavier than air, can accumulate in low-lying areas. In 1986, Lake Nyos in Cameroon released a cloud of carbon dioxide that had accumulated in its depths. The gas flowed down valleys, suffocating over 1,700 people and thousands of animals. Such limnic eruptions are rare but catastrophic. Sulfur dioxide, released by volcanic eruptions, combines with water vapor in the atmosphere to form sulfuric acid aerosols. These tiny droplets reflect sunlight, cooling the planet. The eruption of Mount Pinatubo in the Philippines in 1991 injected 20 million tons of sulfur dioxide into the stratosphere, cooling global temperatures by about 1 degree Fahrenheit for 2 years. Volcanic ash can disrupt aviation. In 2010, the eruption of geological in Iceland produced an ash cloud that shut down air traffic across Europe for days. Ash particles, abrasive and heat-resistant, can damage jet engines. Even trace amounts pose risks. Volcanic ash is not like wood ash, it's pulverized rock, sharp-edged, and capable of melting inside engines. Igneous rocks are classified by their mineral composition and texture. Granite, composed mostly of quartz and feldspar, is light-colored and forms from slow-cooling magma deep underground. Basalt, rich in iron and magnesium, is dark and forms from lava cooling quickly at the surface. Obsidian is volcanic glass, formed when lava cools so rapidly that crystals don't have time to form. Pumice is volcanic rock so full of gas bubbles that it floats on water. It forms when gas-rich magma erupts and depressurizes rapidly, causing dissolved gases to expand and create a froth. Pumice is light, porous, and often used as an abrasive. Intrusive igneous rocks form when magma cools slowly underground, allowing large crystals to grow. Granite, diorite, and gabbro are intrusive rocks. Extrusive igneous rocks form when lava cools quickly at the surface, producing fine-grained or glassy textures. Basalt, andesite, and rhyolite are extrusive rocks. Pegmatites are igneous rocks with exceptionally large crystals, sometimes several feet long. They form from water-rich magma that cools slowly, allowing crystals to grow to enormous sizes. Pegmatites often contain rare minerals, beryl, tourmaline, topaz, lithium minerals, making them economically valuable. Metamorphic rocks form when existing rocks are subjected to heat, pressure, or chemically active fluids. The original rock, called the protolith, recrystallizes without melting. New minerals form and the texture changes. Marble forms from limestone, quartzite forms from sandstone, slate forms from shale. Regional metamorphism affects large areas, typically along tectonic plate boundaries, where rocks are buried deeply and subjected to intense pressure and heat. Contact metamorphism occurs when magma intrudes into surrounding rock, baking it and altering its minerals. Metamorphic rocks often display foliation parallel alignment of minerals created by directed pressure. Schist is a metamorphic rock with prominent foliation and visible crystals. Mica, garnet, and other minerals give schist a shimmering appearance. Gneiss, pronounced nice, is a high-grade metamorphic rock with alternating light and dark bands. It forms under extreme heat and pressure, deep within mountain ranges. Eclogite is a dense, green and red metamorphic rock that forms at depths greater than 30 miles, where pressures exceed 30,000 times atmospheric pressure. It's rarely seen at the surface, brought up only by the most intense tectonic forces. Studying eclogites provides insights into processes occurring deep within subduction zones. The journey from one rock type to another can take millions of years. A sandstone deposited on a beach may be buried by later sediments, compacted into rock, and eventually caught in a tectonic collision. Subjected to heat and pressure, it transforms into quartzite. If buried still deeper, it may melt, forming magma that later crystallizes into granite. Erosion brings the granite to the surface, where it weathers into sand, completing the cycle. Plate boundaries come in 3 types: divergent, convergent, and transform. At divergent boundaries, plates move apart. Magma rises to fill the gap, creating new crust. Mid-ocean ridges are divergent boundaries, marked by underwater volcanic activity and frequent earthquakes. Iceland sits atop the mid-Atlantic ridge, one of the few places where a mid-ocean ridge rises above sea level. Convergent boundaries occur where plates collide. When an oceanic plate meets a continental plate, the denser oceanic plate subducts beneath the continental plate, creating a deep ocean trench and a chain of volcanoes on land. The Andes Mountains form this way as the Nazca Plate subducts beneath the South American plate. When two continental plates collide, neither subducts easily. Instead, they crumple and thicken, building massive mountain ranges. The Himalayas continue to rise as India pushes into Asia. The collision zone is intensely deformed, with rocks folded, faulted, and thrust over one another. Some rocks from the ocean floor between the colliding continents are squeezed upward, which is why marine fossils can be found high in the Himalayas. Transform boundaries occur where plates slide horizontally past each other. The San Andreas Fault is a transform boundary. Unlike convergent and divergent boundaries, transform boundaries don't create or destroy crust, they simply accommodate lateral motion. Earthquakes along transform boundaries can be powerful, as stress builds and releases suddenly. Some plate boundaries are more complex, with elements of multiple boundary types. The boundary between the Pacific and North American plates includes segments that are convergent, transform, and even divergent in places. The Cascadia subduction zone off the Pacific Northwest is a convergent boundary capable of producing magnitude 9 earthquakes. Triple junctions are points where three tectonic plates meet. The Afar Triangle in East Africa is a triple junction where the African, Arabian, and Somalian plates diverge. The region is volcanically active and intensely faulted. Over millions of years, the rift may widen into a new ocean, splitting Africa in two. Rift valleys form at divergent boundaries on continents. The East African Rift is one of the most prominent, stretching thousands of miles from the Red Sea to Mozambique. The rift is marked by steep escarpments, volcanic peaks, and deep lakes. Lake Tanganyika, one of the world's deepest lakes, fills part of the Rift Valley. As rifts widen, the crust thins and eventually ruptures completely. Magma rises from the mantle, forming new oceanic crust. The Red Sea is a young ocean, formed as Arabia split from Africa over the past 30 million years. In another few million years, the East African Rift may follow a similar path, creating a new ocean between Eastern and Western Africa. Subduction zones are among the most geologically active regions on Earth. The descending plate carries water trapped in minerals and sediments. As the plate descends, increasing temperature and pressure release this water into the overlying mantle. Water lowers the melting point of rock, causing the mantle to partially melt. The resulting magma rises, feeding volcanic arcs. The Pacific Ring of Fire owes its existence to subduction. The Pacific Plate is being consumed beneath surrounding plates, creating volcanic arcs in Japan, the Philippines, Indonesia, the Aleutian Islands, and the western coasts of North and South America. These regions experience frequent earthquakes and volcanic eruptions, reminders of the immense forces at work beneath. Accretionary wedges form at subduction zones, where sediment scraped off the descending plate accumulates in a chaotic mass. These wedges contain rocks from diverse sources, oceanic crust, sediments from the deep sea, even fragments of volcanic islands. Studying accretionary wedges helps geologists reconstruct ancient plate boundaries and understand how continents grow over time. Ophiolites, as mentioned earlier, are sections of oceanic crust and upper mantle thrust onto continents during collisions. They provide a rare opportunity to study rocks that normally lie beneath miles of ocean. The structure of ophiolites, pillow basalts on top, sheeted dikes below, gabbro deeper still, and finally peridotite from the mantle reveals the layered structure of oceanic crust. The age of the ocean floor reveals the history of seafloor spreading. The oldest oceanic crust, found in the western Pacific, is about 200 million years old. This is young compared to continental crust, some of which is over 4 billion years old. Oceanic crust is constantly being created at mid-ocean ridges and destroyed at subduction zones, recycled through the mantle on a timescale of a few 100 million years. Continental crust is less dense than oceanic crust and doesn't subduct easily. This is why continents persist over billions of years while ocean basins come and go. Continental crust is also thicker, averaging about 25 miles compared to oceanic crust's 5 miles. The buoyancy of continents allows them to ride high on the mantle, forming dry land. The structure of the Earth can be divided into layers based on composition and physical properties. The crust, mantle, and core are compositional layers. The lithosphere, asthenosphere, mesosphere, outer core, and inner core are defined by physical properties like rigidity and state of matter. The lithosphere includes the crust and the uppermost mantle. It's rigid and broken into tectonic plates. Beneath the lithosphere lies the asthenosphere, a zone where the mantle is partially molten and ductile. The lithosphere floats on the asthenosphere, and convection in the asthenosphere drives plate tectonics. Seismic waves from earthquakes travel through the Earth, revealing its internal structure. Primary waves can travel through solids and liquids. Secondary waves travel only through solids. When seismic waves reach the outer core, S waves disappear, indicating that the outer core is liquid. The inner core, discovered by analyzing how waves reflect and refract within the core, is solid despite being hotter than the outer core. Immense pressure prevents the iron from melting. The inner core is about the size of the moon and composed primarily of iron and nickel. It grows slowly as the outer core cools and iron crystallizes onto the inner core's surface. This process releases heat, driving convection in the outer core and generating Earth's magnetic field. Temperature increases with depth in the Earth, a phenomenon called the geothermal gradient. Near the surface, temperature rises about 25 degrees Celsius per kilometer. Deeper down, the rate decreases. At the boundary between the mantle and core, temperatures reach around 3,700 degrees Celsius. At the center of the inner core, temperatures may exceed 5,000 degrees Celsius, as hot as the surface of the Sunday. Heat flows from Earth's interior to the surface. Some of this heat is primordial, left over from Earth's formation. Some comes from radioactive decay of elements like uranium, thorium, and potassium in the crust and mantle. This heat drives mantle convection, plate tectonics, and volcanic activity. It's the engine that makes Earth a dynamic, geologically active planet. Hydrothermal systems occur where groundwater is heated by magma or hot rock near the surface. The heated water can dissolve minerals and transport them to the surface, where they precipitate, forming valuable ore deposits. Many of the world's copper, gold, and silver mines are associated with ancient hydrothermal systems. Geothermal energy harnesses Earth's internal heat for power generation. In regions with high geothermal gradients, such as Iceland, New Zealand, and parts of California, wells tap into hot water or steam beneath the surface. The steam drives turbines, generating electricity. Geothermal energy is renewable and produces minimal greenhouse gas emissions. Hot springs occur where heated groundwater reaches the surface. Some hot springs are mildly warm, pleasant for bathing. Others are scalding with temperatures near boiling. The chemistry of hot springs varies, depending on the minerals dissolved in the water. Some springs are acidic, others alkaline. Some are rich in sulfur, producing a distinctive rotten egg smell. Travertine is a type of limestone deposited by hot springs and rivers. As mineral-rich water emerges and cools, calcium carbonate precipitates, forming terraces, mounds, and delicate formations. The terraces at Mammoth Hot Springs in Yellowstone are travertine, built layer by layer over thousands of years. Water is a powerful agent of change on Earth's surface. The water cycle, evaporation, condensation, precipitation, and runoff redistributes water around the planet. Water shapes landscapes through erosion, transports sediment, and supports life. Without water, Earth would be a barren, lifeless world. Groundwater, water stored in the pores and cracks of rock beneath the surface, is a vital resource. Aquifers are layers of permeable rock that hold significant amounts of groundwater. The Ogallala Aquifer beneath the Great Plains of the United States supplies water for agriculture and drinking. But it's being depleted faster than it recharges, raising concerns about long-term sustainability. Karst aquifers, formed in limestone regions, can store vast amounts of water, but are vulnerable to contamination. Pollutants can travel quickly through the interconnected caves and channels, reaching wells and springs with little filtration. Protecting karst aquifers requires careful land management. Springs occur where the water table intersects the surface. Some springs flow year-round, fed by large aquifers. Others are seasonal, flowing only after heavy rains. Artesian springs occur where groundwater is confined under pressure, forcing it to the surface without pumping. The water table is the upper surface of groundwater. It rises and falls with rainfall and extraction. In dry regions, the water table can drop significantly, causing wells to dry up. In coastal areas, over-extraction can cause saltwater intrusion, contaminating freshwater aquifers. Permafrost is ground that remains frozen year-round. It underlies about a quarter of the northern hemisphere, mostly in Arctic regions. Permafrost can be hundreds of feet thick and tens of thousands of years old. It contains organic matter, dead plants, and animals that has been frozen for millennia. As global temperatures rise, permafrost is thawing. This releases carbon dioxide and methane, potent greenhouse gases, accelerating warming. Thawing permafrost also destabilizes the ground, causing landslides, collapsing infrastructure, and releasing ancient bacteria and viruses. Pingo are mounds of earth-covered ice found in permafrost regions. They form when groundwater freezes and expands, pushing the surface upward. Some pingos are over 100 feet tall. When they thaw, they collapse, leaving behind circular depressions. Glaciers are rivers of ice that flow downhill under their own weight. They form where snowfall exceeds melting, allowing snow to accumulate and compact into ice over many years. Glaciers move slowly, typically a few feet to a few hundred feet per year, but they're powerful sculptors of landscapes. Alpine glaciers form in mountain valleys. They carve U-shaped valleys, sharp ridges, and cirques bowl-shaped depressions at the head of glaciers. When alpine glaciers retreat, they leave behind moraines, piles of rock and debris carried by the ice. Continental ice sheets, like those covering Antarctica and Greenland, are vast and thick. Antarctica's ice sheet contains about 90% of the world's ice and 70% of its fresh water. If it melted completely, sea levels would rise over 200 feet, inundating coastal cities worldwide. Ice cores drilled from glaciers and ice sheets contain trapped air bubbles, preserving samples of ancient atmosphere. By analyzing these bubbles, scientists reconstruct past climates, measuring temperature, atmospheric composition, and even volcanic eruptions. Ice cores from Antarctica go back over 800,000 years, revealing cycles of ice ages and warm periods. Glacial, interglacial cycles are driven by changes in Earth's orbit and tilt, called Milankovitch cycles. These subtle variations affect how much sunlight reaches different parts of Earth, triggering ice ages and warm periods. The cycles have a rhythm of roughly 100,000 years, with ice ages lasting about 90,000 years and interglacials lasting about 10,000 years. We are currently in an interglacial period called the Holocene, which began about 11,700 years ago. Human civilization emerged during the Holocene, benefiting from the stable, warm climate. Some scientists propose we've entered a new epoch, the Anthropocene, defined by human impact on the planet. Sea level has fluctuated dramatically over Earth's history. During ice ages, sea levels drop as water is locked up in ice sheets. During warm periods, ice melts and sea levels rise. The rate of sea level rise has accelerated in recent decades due to thermal expansion of seawater and melting ice. Coral reefs, often called the rainforests of the sea, are among the most diverse ecosystems on Earth. They're built by colonies of tiny animals called coral polyps, which secrete calcium carbonate skeletons. Over time, these skeletons accumulate, forming massive reef structures. Coral reefs require warm, shallow, clear water to thrive. They're found in tropical and subtropical regions, mostly within 30 degrees of the equator. Reefs provide habitat for countless species, protect coastlines from erosion, and support fishing industries. But they're threatened by rising ocean temperatures, acidification, pollution, and overfishing. When corals are stressed, they expel the symbiotic algae that live in their tissues, a phenomenon called coral bleaching. Without the algae, corals lose their color and primary food source. Bleached corals can recover if conditions improve, but prolonged stress leads to death. Mass bleaching events have become more frequent, devastating reefs worldwide. Atolls are ring-shaped coral reefs enclosing lagoons. They form when coral grows around volcanic islands. As the island subsides, the coral continues growing upward, eventually forming a ring with no central island. Atolls are common in the Pacific, where volcanic islands slowly sink as the seafloor cools and contracts. Limestone islands and cliffs are common in tropical regions, formed from ancient coral reefs uplifted by tectonic forces. The karst landscapes of the Philippines, Thailand, and the Caribbean are sculpted from limestone, with dramatic cliffs, caves, and sinkholes. Fossils in limestone often include shells, corals, and other marine organisms. Some limestones are so rich in fossils that they're essentially compacted seashells. Coquina is a type of limestone made almost entirely of shell fragments, loosely cemented together. Trace fossils, or ichnofossils, preserve evidence of ancient behavior rather than the organisms themselves. Footprints, burrows, bite marks, and fossilized feces called coprolites are all trace fossils. They provide insights into how ancient creatures moved, fed, and interacted with their environment. Dinosaur trackways are among the most spectacular trace fossils. At some sites, hundreds of footprints are preserved, revealing herds moving together. The size and spacing of tracks indicate whether the dinosaur was walking or running. Trackways have been found on every continent, even Antarctica, which was warmer and forested when dinosaurs lived. Amber, fossilized tree resin, preserves organisms in stunning detail. Insects, spiders, and even small vertebrates have been found entombed in amber. The resin acted as a natural embalming fluid, preventing decay. Amber from the Dominican Republic, Myanmar, and the Baltic region is particularly prized for its inclusions. DNA has been extracted from insects in amber, though not from dinosaurs as depicted in fiction. DNA degrades over time, and even in ideal conditions, it's unlikely to survive more than a few million years. The dinosaurs died out 66 million years ago, far too long for DNA to persist. Permineralization is a common fossilization process where minerals fill the pores and cavities of bones, shells, or wood. Over time, the minerals crystallize, turning the organic material into stone. The result is a fossil that retains the original structure but is now made of rock. Molds and casts are fossils formed when an organism's body dissolves, leaving a cavity in the rock. If the cavity is later filled with minerals, it creates a cast, a three-dimensional replica of the original organism. Molds and casts are common in sedimentary rocks. Compression fossils form when organisms are flattened and preserved as thin films of carbon. Leaves, fish, and insects are often preserved this way. The original organic material has been reduced to carbon, but the shape and details remain visible. Mass extinctions are turning points in the history of life. 5 major mass extinctions have occurred over the past 540 million years. Each wiped out a significant percentage of species, reshaping ecosystems and evolutionary trajectories. The Ordovician-Silurian extinction, about 445 million years ago, killed roughly 85% of marine species. The cause is debated, but glaciation and sea level changes likely played a role. The late Devonian extinction, 375 million years ago, particularly affected marine life. Coral reefs were devastated. The cause remains uncertain, but volcanic activity, asteroid impacts, and climate change are possible factors. The Permian-Triassic extinction, as mentioned, was the most severe. The Triassic-Jurassic extinction, 200 million years ago, cleared the way for dinosaurs to dominate. The Cretaceous-Paleogene extinction ended the dinosaurs' reign. After each extinction, life rebounds. Survivors diversify, filling ecological roles left vacant. Evolution accelerates in the aftermath of catastrophe. The mammals, once small and nocturnal, diversified after the dinosaurs vanished. Primates emerged, and eventually, humans. The history of life is a story of resilience. Despite repeated catastrophes, life persists, adapts, and innovates. From single-celled organisms to complex ecosystems, life has transformed Earth, shaping the atmosphere, oceans, and land. Let your thoughts settle like sediment at the bottom of a quiet lake, each layer a moment in time, each grain a story, and you, here, now, part of the ongoing story of this planet. Gemstones are minerals prized for their beauty, rarity, and durability. Diamonds, rubies, sapphires, and emeralds are the precious stones, though many other gems are equally stunning. Tanzanite, found only in Tanzania, displays vivid blue-violet hues. Alexandrite changes color depending on the light green in daylight, red in incandescent light. Turquoise, prized for millennia, forms when copper-rich water percolates through aluminum-rich rock. Its distinctive blue-green color comes from copper. Turquoise from the American Southwest was traded across ancient North America, valued by indigenous cultures. Jade refers to two different minerals, jadeite and nephrite. Both are tough, capable of being carved into intricate shapes. In China, jade has been treasured for over 5,000 years, symbolizing purity and moral integrity. The finest jadeite, called imperial jade, is a translucent emerald green. Pearls are unique among gemstones. They're produced by living organisms. When an irritant enters a mollusk, the animal coats it with layers of nacre, or mother of pearl. Over time, a pearl forms. Natural pearls are rare, but cultured pearls, grown with human intervention, are widely available. Lapis lazuli, a deep blue rock, has been prized since ancient times. It's not a single mineral, but a combination of lazurite, calcite, and pyrite. Ground into powder, lapis lazuli was used to make ultramarine, a pigment used by Renaissance painters. Malachite and azurite are copper carbonate minerals with vivid green and blue colors. They often occur together in copper deposits. Both have been used as pigments, and malachite, with its distinctive banding, is popular in jewelry and decorative objects. Moonstone displays a phenomenon called adulorescence, a soft glowing sheen caused by light scattering within the stone's layered structure. Labradorite shows a similar effect called labradorescence, with flashes of blue, green, and gold. Garnets are a group of minerals that come in many colors, though red is most common. Some garnets change color under different lighting, similar to alexandrite. Garnets are found worldwide and have been used in jewelry for thousands of years. Topaz is a hard, durable gemstone that occurs in many colors. Blue topaz is popular, though most blue topaz on the market has been heat-treated or irradiated to enhance its color. Imperial topaz, a golden-orange variety, is particularly valuable. Amethyst, a purple variety of quartz, has been treasured since ancient times. Its color comes from iron impurities and natural radiation. Large amethyst crystals can be found in geodes, their purple interiors sparkling in the light. Citrine, a yellow to orange variety of quartz, is less common than amethyst. Much of the citrine on the market is actually heat-treated amethyst, which changes color when heated. Peridot is a green gemstone formed deep in the mantle and brought to the surface by volcanic activity. It's one of the few gemstones that occurs in only one color. Peridot has been found in meteorites, making it one of the few extraterrestrial gemstones. The ground beneath you has been shaped by forces operating over unimaginable timescales. Mountains rose and fell, oceans opened and closed. Continents drifted like ships on an endless voyage, and through it all, life persisted, adapted, and flourished. Geology teaches patience. A single human lifetime is a blink in the life of a mountain, a heartbeat in the story of a continent, and yet we are here. We stand on the shoulders of ancient stone. We breathe air shaped by billions of years of life. We are witnesses to a planet still evolving, still changing, still creating wonders. So wherever you are, allow your mind to rest. Let your breath slow. Let your thoughts grow soft at the edges. The earth turns beneath you, patient and enduring. The mountains stand, the oceans flow, and you, for this moment, are part of that great, quiet rhythm. Sleep well, and thank you for wandering with us through the deep history of our world.